This is Mrs. O'Neill for AP Chemistry, Chapter 19, Section 4, Entropy Changes in Chemical Reactions. In this section, you're going to use a table of standard molar enthalpies to calculate the standard entropy change for the entire reaction. So pause, fill in the blanks, and then play to hear my words. So standard molar entropies is the molar entropies of all substances at their standard state. So that's going to be a little different. It doesn't say STP, it says standard state. So when we look at an example of a list of substances with their entropy, let's look at some of the conclusions, some of the differences that you might see here that's different than what you've seen before. So first, the temperature reference is at 298 K, which is basically room temperature. It's not at 0. It is not at STP. So we want to keep that in mind. The other thing to look at is, again, gases are going to have a greater S value, a greater entropy, and you saw that in the last video, how gases are going to have more entropy, more disorder than your liquids and solids. So let's look at a specific example, like your liquid water is 69.9, but your vapor, or H2O as a gas, is 188.8. So again, there's an increase in entropy as you go from that solid to a liquid to a gas. Entropy increases with increasing molar mass. So if we look at something like two elements like lithium and potassium, lithium is 7 grams, potassium is 39 grams. As we increase molar mass, we're increasing the entropy. We are increasing the number of atoms or the complexity of a substance. We're going to increase the delta else as well. So this should make sense. So if you have sodium, 1 atom, 51.4, you have 2 atoms together making a compound of 72.3, and then you have something like CH3OH, besides the fact that it's liquid, but also you have multiple atoms now together making that huge complex compound, lots of molar mass. You have a huge delta NS value. You have a huge molar entropy value. The last thing to bring to your attention is the joules. Delta H and delta G, when we talk about them, is going to be in kilojoules. S is going to be only in joules. So when there's going to be an equation that relates all three of them together, we got to make sure that we convert our joules to kilojoules or kilojoules to joules before we deal with the equation itself. Okay, so hopefully that makes sense to you. And again, delta S or entropy is about disorder, increasing in disorder. So how does this affect the temperature? Again, the entropy is going to change the surroundings, and it's determined by that heat flow. I want to remind you that heat always flows from a warm object to a cold object, and this is why exothermic processes are usually favored. They are usually thermodynamically favored. They are usually spontaneous. And I say usually because, again, we have those few exceptions to the rule where an endothermic process is favored, but not usually by much. So how does this change? I would pause the video and just make sure you're understanding what happens to the enthalpy, that's delta H, what happens to the entropy, and would the reaction be spontaneous or not. So if we look at something like this, right, ice is going to turn to water. Yes, it is going to happen on its own. It's going to be spontaneous if the temperature is greater than 0 degrees Celsius, which again, for most parts or most of the time, ice is going to melt spontaneously because usually ice is in a temperature greater than 0 degrees. However, if that temperature is less than 0 degrees Celsius, it's not going to be spontaneous. There's no way you're going to take that ice cube and turn it into water if the temperature is less than 0 degrees Celsius. So the same thing the other way, right? If the temperature is greater than 0 degrees Celsius, water into ice would not be spontaneous. It's not going to happen. But if the temperature is less than 0 degrees, it's going to happen on its own. So this is going to be temperature dependent. Okay, spontaneity is going to be temperature dependent. So the sign of your surroundings is going to depend on the direction of heat flow. And again, so when we see delta S of the surroundings being positive, it's going to be exothermic, and if it's negative, it's going to be endothermic. And we always want to remember delta S, any kind of delta S, if it's positive, it's going to be surroundings. So we're talking about, is it exo or endothermic, and at what temperature? So that's the equation to kind of think about. So again, let's look at this. Let's look at the thoughts on that equation, that negative delta H over T. So just kind of, again, briefly look over this, pause the video, see if you're understanding how that all plays together. So give it some thought. Again, read over that, and that Q of that system is basically your delta H. Kind of the same thing if you remember from chapter 5. So here's an example. Which has greater disorder, the reactants or the products in this reaction? So the first thing I would look at is they are all gases. So we can cancel that out. What would be the next thing we're going to look at? Maybe the number of moles. So we have 4 plus 5 over here and 4 plus 6 over here. So if we have 9 moles versus 10 moles, the disorder is going to increase, making the delta S positive. So it's going to be spontaneous. We want to remember, again, disorder. An increase in disorder is an increase in entropy. More complex of a molecule, more entropy, more disorder. More molar mass, more disorder, more entropy. It increases as we increase molar mass. Very similar to polarity or polarizability. We talked about polarizability chapters ago when we talked about shapes. I believe that was chapter 8 or 9. So again, kind of the same concept. As we're increasing our molar mass, as we're increasing our polarity, as we're increasing the complexity, we're increasing the disorder of that molecule. So pause the video, see if you can figure out A, B, C, D. Is 1 mole of NaCl solid going to be higher or lower entropy than the 1 mole of HCl gas? And you also want to give the reason why. Again, that's going to be really important on the AP exam. They always want you to justify or explain your answer. So pause the video and see if you can do your answers with the why. So hopefully that makes sense. If it doesn't, again, you can ask me or anybody in class when we're doing the book work. You've seen this before. If we take the delta S of the reaction is going to equal the number of moles of your products minus the moles of your reactants, and you're going to subtract that whole thing. So it's products minus reactants like we've done before. So you have your S values. You'll be given some kind of chart. Okay, so if we look here as example 1, I'm giving you the S values for the 3 substances in the reaction, but we want to remember this would be multiplied by 1, the H would be multiplied by 3, and the NH3, the ammonia, would be multiplied by 2. So put your numbers in. See if you can do this without even going through the example, because again, you've done this before. Products minus reactants, just make sure that your numbers are multiplied by those coefficients. So here's our solution. So products minus reactants. Here's our 2 ammonia minus the 1 nitrogen plus the 3 hydrogens. Plug and chug your numbers. And again, at this point, if you didn't get here or you don't have the correct numbers, pause and see if you can calculate it correctly doing the math. Should have gotten a negative 198.24. And again, this is joules per Kelvin mole or joules per mole Kelvin. It really doesn't matter, but it is in joules and not kilojoules. So, and again, according to sig figs, you would only need 4 numbers there. Entropy is going to decrease because there are less gas molecules in the product. So again, that makes sense. We have 4 gas molecules as reactants. We have 2 as products. So your entropy actually goes down, and that's why there's that negative there. So that should make sense. Okay, try number 2. Again, your S values are should be on your paper, on your notes packet. If not, it's on the next slide. So there I'm giving it to you just that way, just listing the numbers underneath each of those substances. Now we're just going to products minus reactants. Plug and chug our numbers. And again, I did it step by step because sometimes that's easier than putting it all in your calculator and getting messed up. And we get a number of negative 148, actually 0.0 according to sig figs. And again, entropy is going to decrease. Let's look here again. We have a solid here and a solid here. So we have 2 solids and 2 solids, so we're going to cancel that out. But we have 3 gas versus 2 gas, and that's where the entropy decreases. Or you could also say that the order, right, it's becoming more ordered, and that's why there's entropy decreasing. Okay, see you in class.